In water management and hydraulic engineering, you often have to deal with water basins that are connected to an external water system by means of a channel or a hydraulic structure. Think of, for example, a lagoon that's connected to the sea by a tidal channel, a reservoir for drinking water in connection with a river, or a polder that's flooded through a breach in the dike. In this video, we will first take a look at a practical example, the waterdunen, after which we will consider a problem for which we have to create a mathematical model. In all these cases, the water level in the basin and the discharge in the inlet are influenced by the water system to which it's connected. If the water level in the latter changes, for example due to the tide or a river flood wave, the water level in the basin also changes, and there is a flow in the inlet. Many of such areas are relatively small compared to the length of a tidal wave, which are several hundreds of kilometers long. The water motion is then easy to understand and simple to model. In concrete terms, we are talking about areas with a horizontal size of approximately 10 to 20 kilometers. As an example, let's visit the Waterdunen, a newly created nature reserve in Zeeuws-Vlaanderen, an intertidal area. It consists of a maze of creeks and shallows and is surrounded by a high dike that serves as a flood defense. Underneath this dike, at the side of the Western Scheldt, a culvert has been constructed through which seawater can flow in and out of the area. In this way, the tide in the Western Scheldt influences the Waterdunen, causing a current through the culvert and an up and down going motion of the water level in the creek area. By adjusting the position of the slides in the culvert, the tide in the Waterdunen can be regulated. This is important for the natural area. Think of the flooding and drying of shallow parts for foraging birds and the supply of sediments and nutrients for the growth of all kinds of plants and animals. We therefore want to be able to predict the water motion in the area. Also, when restoring a dike around a flooded polder, such as after the storm surge event in 1953, or when an estuary is closed off, the tide in the area must be predicted. Because of the tidal water level variation at sea, the discharge in the closure gap varies over time. The material used for the closure, usually sand or rubble, will wash away if the resulting flow velocity is too large. The gap must therefore be closed when the discharge through it is minimal, preferably zero. We want to predict at which time instant this situation occurs. All equipment needed for the closure must then be ready. A recent example concerns the sand closure of an inland lake during the construction of the Tweede Maasvlakte. The Queen was invited for this event, and of course, you don't want her waiting for hours for nothing. We will use this so-called closure gap problem as an example. The model that we will derive for this is much more widely applicable, but more about that later. The flow through the gap experiences resistance. The discharge is therefore dependent on the water level difference between the basin and the sea. The water level at sea is continuously changing due to the tide. The water level in the basin also moves with the tide at sea, but lags behind as the water must first pass through the gap. We are now going to derive a mathematical equation to describe this situation. The mathematical model describing the flow through the closure gap is a differential equation. You can compile this from two equations, the volume balance and the discharge relation. The volume balance states that the discharge Q through the gap equals the rate of change of the water volume V in the basin. The change in the water volume can in turn be expressed as the change of the water level H in the basin times the area of the basin, AB. That surface is not necessarily the same for all water levels, but a mean effective value has been assumed here. You also see that the flow through the gap is 0 if h doesn't change, so if the level in the basin has a maximum or a minimum. The second equation that we use is the discharge relation for the closure gap. How easily does the water flow through the gap? First of all, the discharge in the gap depends on the difference between the water level at C, HC, and that in the basin, H. When the water level at sea is lower than that in the basin, water flows from the basin towards the sea, and the discharge Q is negative. The water also experiences resistance when it flows through the gap, which depends in a nonlinear manner on the shape of the gap and also on the magnitude of the flow velocity. For our example, we can linearize this relation, giving this expression, in which c is a constant coefficient having the unit of square meters per second. Equating the two expressions for Q now gives this equation. Now divide everything by the coefficient c and move h to the left-hand side. Defining the so-called relaxation time tau as AB divided by c, we get this equation. In our case, the tidal water level at sea varies harmonically with a period of 12.5 hours and a vertical range of 2.4 meters. The properties of basin and gap are such that the relaxation time tau has a value of 2.2 hours. We thus obtain the following differential equation for the water level in the basin.